This is the third of several recordings in which I am calculating the Laplace transforms for a number of useful periodic functions. Here I'm looking at the triangular wave. I've drawn an example of such a wave here. In my example I've chosen the amplitude to be 1 and the period to be 4. You could choose different values for these quantities if you wish, but you'd have to make some changes in the integrals that follow. The first thing we need to do is to identify the basic unit of the function and then describe it with a functional rule. I'll take the basic unit to be the first triangle, that is, the one extending from t equals 0 to t equals 4. We're going to need to describe it in two sections, the left-hand side and the right-hand side. That means f of t will have a piecewise description, from 0 to 2 and then from 2 to 4. Let's start with 0 to 2. The function rises through a height of 2 and it also runs across to the right a length 2. That means that the gradient is 2 over 2, the rise over the run, or 1. So the functional rule must contain just t. We then need to add a constant in order to make sure it goes through the right points. The correct rule for this part of the function is f of t equals t minus 1. For the right-hand side of the triangle, we now drop the same level over the same distance. So the gradient is now negative 1. This part of the function must have negative t in, and the correct constant is 3. I've also written down the periodicity rule, but it repeats every 4 units. Okay, what about the Laplace transform? Well, do you remember we have to integrate just over the one period, that's 0 to 4, but with a factor at the front that compensates for all the missing parts of the domain that we haven't integrated over. It looks like this. The period 4 appears in that factor at the front, in the form e to the minus 4s. Now unfortunately, even on the interval 0 to 4, our function f still has two different rules, so we now have to split that integral up into two parts. The part from 0 to 2, where we can write f of t equals t minus 1, and the part from 2 to 4, where f of t is 3 minus t. It looks like this. You can see these expressions are starting to get a bit cumbersome, so from now on I'm going to leave off the factor at the front just for the moment, and at the end I'll put it back. The integrals themselves just require integration by parts. I'm going to do that now. You can halt the recording and check my integration if you wish. Assuming you're happy with those expressions, look at the parts with s squared in. They're the same, aren't they? On the left-hand side, the integration limits are from 0 to 2, and on the right-hand side from 2 to 4. Since 2 is a top limit in one and a bottom limit in the other, it will contribute with opposite signs. That means there will be some cancellation. We might as well take that into account straight away. That term, instead of being substituted twice, could be written as 1 over s squared e to the minus st just from 0 all the way to 4. The other two terms, of course, must retain their correct integration limits, so I've written those out first, and then that 1 with s squared I've put at the end, evaluated all the way from 0 to 4. I've now got to substitute the limits in. To make it easier for you to check, I've taken the top limits and written the terms in blue, and the bottom limits I've written in red. This is what I get. Let's now collect the terms that have s squared and those that have s. It's beginning to look a bit more manageable, isn't it? The first term there is already in a form that I like very much. The second term we can do some more manipulation on. Can you see that it's a perfect square? In fact, it's the square of 1 minus e to the minus 2s. Now I'm going to manipulate that second term by multiplying it by 1 in a very special way. In fact, by e to the 2s over e to the 2s. The e to the 2s on the bottom is going to stay there, but the one on top can be taken inside the parentheses where it's squared. Of course, when we take it inside, because of the square outside, it must be changed to e to the 1s. If I do that all in one go, I can then multiply the e to the 1s by the 1 and by the e to the negative 2s. I get the following expression. You can maybe now see why I've done that. That expression on top is in a moment going to turn into a hyperbolic sine, a shine. Let's remind ourselves about the shine. There's the definition on the left in red. So that thing that we have on top there is actually the square of 2 shine s. Let's include all that information in the next line. Okay, nearly there. But remember, this was just the integrals. We've still got that term at the front that we've got to divide by. Do you remember what it said? It was this one. 1 over 1 minus e to the minus 4s. Ah! Look at that first term. The 1 minus e to the minus 4s is going to cancel there, isn't it? The other term, of course, will still have it underneath. But actually, we can now do something else. We can multiply out the brackets on the bottom. And now we see that we have a shine there again. In fact, it's 2 times the shine of 2s. So let's put that in. See, there's a 2 missing there. But now I remember there's a formula for double the argument. Shine of 2s is the same as 2 times shine s cosh s. It's very much like the trigonometric one. That makes an overall factor now of 4 on the bottom. And with shine s cosh s, we see that one of the shines cancels on the bottom and the square on the top. The 4's also cancel. So this expression has simplified down very much, because what's left is just shine over cosh, which is the hyperbolic tan. I think this is the best form for the Laplace transform of the triangle wave. I'm going to finish there.